no difference between the machine learning, what we understand today, and statistics, what we used to study a long time back and studying and so on and so forth here. So in terms of definition, there is no difference. So the first question, which at least I was not clear, that if both things are same, they are studying, trying to understand the same type of problems, then why we are having two different topics? So for that, you have to proceed to the next slide. So we have seen that in machine learning, we studied data classification. Now, this is not a new problem. Fisher studied in 1936. So discriminant analysis for data classification, that is a very famous Fisher work, and that he did in 1936. What we are talking about, the pattern classification in machine learning, essentially has been studied earlier in 1936. Similarly, the regression model, which we try to study, modeling and prediction, it is not something new. Gauss has studied in 18th century, late 18th century. So again, there's a problem. The type of problems we are studying today have already been studied long time back, and still we are saying that we are learning machine learning and this topic and that topic and so on and so forth. And therefore, that leads to these two questions. How is machine learning different from statistics? That's the first question. Because statistics we know from our a long time back. Machine learning has become fashionable now. Everybody is using it actually here. So the first question is how these two are different topics. And second thing is, as some of the stations are saying, that machine learning is nothing new. It is nothing but glorified statistics. So is it correct? So that means we want to understand that how does machine learning differ from statistics? And if somebody says that machine learning is glorified statistics, is it justified or not justified, and so on and so forth. Now, what the conclusion, at least I feel, is that machine learning and statistics, they try to, sorry. Yeah, they discuss the same type of problems, but there is a vast difference, and the difference is in terms of goals, methodologies, and so on and so forth here. So let's try to see that what is the difference between these two topics are there. So for that, actually, we have to understand these two topics. So one is what is called the statistical learning theory, in short SLT, and the other is what is called the reproducing kernel Hilbert spaces. These are two main topics in machine learning, which try to make us that how it is different from statistics as such, and how they are too general, more general than what we study in statistics. So although statistics and machine learning, they try to understand, discuss same type of problems, but the basic assumptions and other things that they are vastly different. So that means if somebody asks, at least me, that what type of mathematics I should understand, then obviously we should know probability and statistics. Only then probably we understand this topic. And then if you want to make use of kernel trick, what we have learned and so on and so forth here, we have to understand what is the meaning of reproducing kernel Hilbert spaces. And that simply means you have to understand what is the meaning of Hilbert space. Now, to know Hilbert space, of course, so you know a lot of things, vector space, inner product space, and so on and so forth here. So that is the bare minimum if you want to understand the machine learning from mathematics point of view. That is, understand probability in the statistics, understand optimization, and understand analysis and linear algebra. So linear algebra, analysis, probability in statistics, and optimization. These are the four pillars of the mathematics which ultimately support the understanding of machine learning. Now, in this talk, I will simply stick to how does the theory enters in classification problem. I will not go to the regression problem and also not discuss the neural networks. So, but these things are available. So once we understand that how what is the learning theory for the classification problem in machine learning, we can certainly translate most of things for regression problem and the neural networks and so on and so forth here. Something which is not clear at present is from mathematics point of view, that how does this theory work for deep learning. So the mathematics of deep learning is still not fully clear. I mean, it is a very well-developed topic now. Everybody is using it here. But theoretically, deep learning is not understood at present here correctly and completely. Now you are given the data. So we have seen that you are given data and you want to learn. So this is your what you call a training set. So training set this is a vector, and this is, if it is a classification problem, it is a class label. So if it is a binary problem, then class label is -1 or 1. If it is a regression problem, then of course it could be a real number. So because we are saying about classification problem, so you are given L vectors in Rn, and you are given the class labels. So y1, y2, yl, these are class labels. So every data point has a class label as +1 or -1. What is our goal? Our goal is that you want to learn. So given this data, you want to learn, and then given a new input X, I want to predict its output. I want to predict its output. That's what the goal is. That simply means that essentially you want to identify a function from Rn to the y. Y, you remember, that is nothing but 2 points set -1 and 1, which is a good approximation of the output for an arbitrary X. And that means you have to understand what is the meaning of good. So when you will say that my prediction is a good prediction, so that means the meaning of good has to be understood. And so for that, actually, you have to make certain assumptions. And these assumptions you have to make with regard to the training point and with regard to the new point on which you want to make prediction. Now, the statistical learning theory makes the following assumption. The assumption is, this is a very basic assumption. This assumption is that training points and that is the training set and future points xy are independent, ideally distributed random variables generated from a unknown but same fixed probability distribution pxy. So the first assumption which is being made about the application of machine learning for any problem is that your training data points and the points for which you want to make a prediction, that is test points, they must come from the same population, having the same fixed probability distribution function. The important point here is that distribution function is there, but the machine learning does not require you to prescribe distribution. That is the main difference between machine learning and statistics. In statistics, we always say that data is given from normal population, Poisson population, and so on and so forth here. So for any statistical method to work, whatever data you are given, you have to identify, you should be given the corresponding probability distribution function. The machine learning assumes that the training points and data points are given to you. They have come from some population, but we don't bother about the exact form of this probability distribution function. Technically, it is called that machine learning is distribution free. So the main difference between machine learning and statistics is that statistics is distribution dependent, whereas machine learning is distribution free. There is some distribution from which the data points have come. We do not bother what that distribution is. In statistics, you would bother it. You have to say that that data point has come from normal distribution, Gaussian distribution, so forth. If you don't know this distribution, you try to fit it. So there's the goodness of fit and so on and so forth here. But you cannot proceed any statistical algorithm for the given data set without identifying its probability distribution function. In machine learning, there is some probability distribution function is there, but you don't bother what that distribution is. That is the main difference, and that we must always keep in mind. So statistics is distribution dependent, machine learning is distribution free. So that means if I want to define machine learning in one sentence, I will simply say that distribution free is statistics in machine learning. So as soon as you make statistics free of distribution, it is nothing but the machine learning from the mathematics point of view. Now, so this is how it is generated and so on and so forth here. So this is a very important assumption, and we must never forget that if you are using machine learning, then you have to bother that the data point and the test points, they are all coming from the same probability distribution function. Now, this point has become very important because now if you see, there are some papers which are dealing with, suppose you are given a very small data set. So if you are given a very small data set, then there are methods to generate more data sets, and then in large data sets, so that you can use the machine learning algorithm as such and so on and so forth. So for example, if you are given a very small data set, then it will not work. So there are now techniques very recently in the last 2-3 years which enlarge data set. Now, if anybody enlarges data set, it is important that whatever method you are using for enlarging data set, you must make sure that new data points which you have generated and the old data points which you are given all must come from the same probability distribution function. Because if this assumption is not made, not hold, then the machine algorithm will not be used actually. Okay, so there is some sort of uncertainty because you are given only the data and you want to predict the function. Now, actually, in mathematics, we have got two types of problems. That you are given the input, you are given the function, and you can find out the output. So if I know the function, if I are given the input, I can find out the output y is equal to fx. These problems are called direct problems. Then there are other problems that you are given input and given output, you want to find out the function. These are called inverse problems. So this is what is happening here. You are given the input and you are given the output, namely this yi, and you want to find out the function. That means given the input, given the output, you want to find out function what is sitting inside. These problems are called inverse problems. So most of mathematics deals with direct problems. Given the input, knowing the function or dynamics, you can predict the output. So that the function may be solution of differential equation, integral equations, matrix, and so on and so forth. Those are the typical mathematics studies only direct problems that given the input, given the function, determine the output. In that sense, it is totally different from the general terminology or general approach of mathematics. Here, these are inverse problems. You are only given the input, given the output, and then you want to find out what is sitting inside. You want to find out this function f. If the function f you can find out, then you can do the classification, regression, and so on and so forth here. And this function you want to determine on the basis of this given training set. So the second difference is between mathematics and machine learning is that mathematics deals with direct problems, machine learning deals with inverse problems. Now, because it is an inverse problem, therefore there is no guarantee that the solution will exist. There is no guarantee that the solution will be unique. So that means all that in mathematics you've got what is called the well-posed problem and ill-posed problems. So the machine learning is a very, very ill-posed problem because we don't know anything about the function f. Knowing only simply the input and output, we want to find out the function f. So the first difference between machine learning and data and mathematics is that machine learning mostly deals with direct problems, but machine learning problems inherently are ill-posed problems, and therefore they are more difficult to handle. Now, if the problem is ill-posed and data has come from some probability distribution function, so on and so forth here, no matter what function you choose, there's always a risk of making the wrong choice. Now, the question is how do you measure the risk? Now, risk is always with respect to loss. So, for example, if you are investing in some amount in the market, then you are taking risk, and that risk you are measuring in terms of loss which will incur by losing the share money and getting the share money and so on and so forth here. So, theoretically, whenever you want to quantify what is the meaning of risk, there has to be a concept of loss function. So now the question is that because the things are uncertain, data has come from a typical probability distribution function which you don't know. I want to determine an f which will solve my problem, what is the classification problem or regression problem. Because things are uncertain, I am open to risk. Now I want to measure that risk because only then I will be able to minimize that risk. I will choose that f for which that risk is minimum. To measure the risk actually here, you have to identify a loss function, because unless you know what is the loss function, you won't be able to quantify the risk. By definition, risk is nothing but the average value of loss function. So once you choose a loss function in a given situation, then immediately you can calculate the risk. And then once you know the risk, now we understand in our mind, solving such a problem is simply identify loss function, identify risk, and choose that function f for which this risk is minimum. So conceptually, we are clear. Of course, things are still not simple, as we shall see proceed and see and so forth. So what is a loss function? So loss function is simply a function from Rn cross y. So it is simply a triplet. That means if I take an input x and then I take a corresponding y here, I have the value of this function here. Loss function associates a positive loss. So loss cannot be negative. Either it is 0 or infinity. It is 0 only when the output matches the prediction. So the loss function essentially is a function which says that if your prediction is same thing as output, then the loss is zero. Otherwise, the loss is positive. Of course, from practical point of view and algorithmic point of view, we also assume that the loss function is continuous, loss function is convex, and so on and so forth here. But theoretically, loss function is simply a function which associates the value zero if the prediction is equals the output, otherwise the loss is positive. Now there are so many loss functions are there that we shall discuss in a moment actually here. Now once the loss function is given to you, I can define what is the meaning of risk. So this R denotes the risk for any function which you've chosen. Yeah, our aim was that given a data set, given a training set, I wanted to choose that function f. For choosing that function f, we have agreed that we shall choose a loss function, determine the risk, and then choose that function f for which this risk is the minimum. Now, what is the risk? This is nothing but the average of loss functions. So that means because it is a maybe continuous function as well, therefore there is nothing but an integral over this domain, loss function this, and corresponding probability distribution function, dp of xy. So we know what is a loss function, and once we understand the loss function, the meaning of risk simply means the average value of risk or expectation of risk. Now that means our aim is now to choose that f for which this loss function, this risk function is minimum. Now there is a very major difficulty now here, because this risk function depends upon p, and our basic assumption is that p is not known to us. We have not bothered to understand what is the probability distribution function population from which the data has been drawn. So p is not known to me. Once p is not known to me, even if you have made a choice of L, I cannot evaluate this integral and get the value of RF. That simply means, although the problem looks simple, still it is extremely hard because we cannot evaluate this function f, R. And once you cannot evaluate the function R, there is no way of finding out the function f. So the question is that what should we do now? Okay. So that means risk is simply nothing but the average loss function that we've seen already. So this is your binary classification problem. This is the probability P from which you have come. This is loss function you have chosen, and RF is expected risk. And our goal is to determine the decision function f for which RF is minimum, so that we have understood. Now this is the main difficulty. Again, I have mentioned it. Since the probability distribution function P, which generates the training set and the unknown pair x at y at, the expected risk of the decision function, namely RF, is not computable. And consequently, it is impossible to find the decision function f by minimizing the true risk R of f. So because P is not known, RF cannot be computed. When RF cannot be computed, you cannot find out the function f. So you are trying to attempt something which is impossible to attain, simply because the P is not known, therefore RF is not known, RF is not known, therefore you cannot find out f actually. So what we should do now actually here? Okay, so what to do get this desired f? So we must find some computable and reasonable approximate substitute to replace the two RF here. That means we should try to find out something which is based on data and see that how far that is good approximation for the risk which you don't know. And this is what is precisely called the empirical risk. The empirical risk is supposed to give you the true approximation of the actual risk. Why I'm saying supposed to? Because there are certain points are there. It will not do actually. It will be very near, but not exactly approximation. So empirical risk is something you are trying to define so that you have got some idea of the true risk and then minimize that to obtain the corresponding f. What is the empirical risk? Empirical risk is very simple. You are given the training data here, and the loss function you have already chosen. Therefore, this quantity is also known to you. For every xi, yi, I know what is loss function is there. So this is your empirical f. So for a given f, I can find out what is this expression is, because it depends upon only on the training data, on the function which you are proposing, and the loss function you chosen. So everything is known to me here. So for a given f, I can find out our empirical f. So empirical f, I can compute risk or empirical risk for a given f. I can evaluate knowing choosing the last function and then choosing the function f. So what should we do now actually here? That means now we got a very nice idea that empirical risk I can compute. Therefore, choose a decision function f for which empirical risk is minimum. So this is what is called the empirical risk principle. So that simply says that you compute the empirical risk, choose the family of functions f. In that family of function, you choose that f for which empirical risk is minimum. For empirical risk is minimum. Okay. So that means the thing is that we cannot compute the actual risk. For that, we have tried to define what is the meaning of empirical risk. Empirical risk I can compute for every f once I make a choice of loss function. And then empirical risk principle says that choose that f for which the empirical risk is minimum. So you can take an example for example here. Okay. So this is saying that the question was that how big this f could be. Can I choose the all functions? The answer is no, because if you choose all functions, then you are going to have the overfitting. In terms of simple thing, it basically means that given training data, I want to fit a model. Now, will that model should be too simple or it should be too complex? Because if it is too simple, it will not explain the training data, and if it is too complex, then although it will explain the training data set very well, it will not give good approximation for the new unseen data. So that means you have to do some sort of compromise between the that how should model be simple or difficult. Now, in common sense language, that simply means you must try to have compromise between underfitting and overfitting. Model should not be as simple that it fits every point, and it should not be that complex that it should not be that simple that it doesn't fit the given training data, and it should not be that complex that it fits every data points and gives a bad approximation. So that means essentially you are thinking of finding out function f such that it does compromise between underfitting and overfitting, or between the two aspects, that how simple is the model and how difficult is the model. So we don't want to find out the function f, that is the model f, for which is too simple, which is neither too simple, not so difficult. And for that, you understand what is the meaning of saying that the model is not so difficult. For that, you understand what is the meaning of model complexity, and that is something which we proceed now here. So what ERM principle says that given a training data set here, given this loss function L, and choose a class of function script f, in such that you evaluate this function f for each f here, and then choose that function f for which the empirical risk is minimum. So this is what is the empirical risk principle is. Now you want to know what is the connection between empirical risk and true risk. Remember, it is your empirical risk and this is your true risk actually here. Now, essentially, we all have read. So in statistics, we use least square regression and so on and so forth here. So whole of the statistics is basically based on empirical risk minimization principle. Simply because of the reason that you know probability distribution function, and once you know that, then empirical risk for large sample, large data, the empirical risk will always give you the true risk actually here. So the law of large numbers essentially tells you that for each single f, this probability, this limit is equal to 0. There's a mistake here. No, it's fine. Yeah. That means in terms of probability, they say that as n goes to infinity, this is L rather here, it is not n, it is L, the data points. It goes to infinity, then probability that these things are more than epsilon, this probability goes to 0. So law of large numbers tells you that for large data size, the empirical risk is a good approximation for the true risk, provided this f is fixed. Please try to understand. The law of large numbers gives you this property for a fixed f, but the true risk is defined for every f. You want it is over the whole family of f here. So it is a nice thing, but it is not the ultimate thing. Simply because the reason that some of you in mathematics must have understood that, that if you are given a sequence, you got if it is convergent, you got pointwise convergence, and you are given the I will just get a glass of water, please. Pardon me. Sorry. So what I was trying to say that this convergence is only point-wise, whereas you want the uniform convergence. That means now you change the criteria a little bit and try to understand that it is good, but it is not enough. So what is next thing we want to understand? Let's try to see. I have some examples here. So, for example, this you might have seen in the earlier talks that you're given this training set, and if you take the in-loss function, then you can compute the. I think this had been done in the morning class actually here, so I won't go into the detail. But what actually really happens that if you take the compute the imperialist minimization principle here, then you get a problem of this type here. So for a binary data classification problem, this is what is called the empirical risk minimization problem. So you can find, given data points, I can find out this problem, solve this problem here. It is a linear point problem. I can solve that actually here and get W and B and get the classifier. So these things are written in the morning class, so I won't go into those details. Okay, so when a number of data points is small, empirical F does not lead to good approximation of true risk. So that means even if I fix F and I make data points large, then of course for a fixed F, this will converge to this one. But if data point is small, then even for fixed F, this is not going to happen. But the difficulty was that it is not a question of a small or big data size. The question was that I wanted this approximation to be nice for this one for all points, all functions in the family. So whereas it is only point-wise, for given F, this thing is true. If I choose the entire class, then this thing may not be true. Okay. What it means here that if I consider the empirical risk here, I minimize that and corresponding to see that the corresponding solution will be F empirical. Whereas if I choose the true risk, then this may be minimized at some other point, F minimum. And F empirical may not tend to F minimum as the sample size becomes large. So that simply means there is no guarantee that the empirical risk will converge to the true risk for all functions in the entire family. It will converge if the function is fixed, but I want that it should converge to all points in the entire family. That's not going to happen. In other words, simply says that ERM principle is point-wise convergence, whereas we want uniform convergence. So I want uniform convergence, but empirical risk minimization principle is not giving me that. So ERM principle is applicable only when number of training points is large. If when number of training points is small, then we need to assume the data has come from multivariate normal distribution. In any case, irrespective of data size or normal requirement, the convergence in ERM principle is not uniform, it is only point-wise. That means the traditional statistical methods are based on ERM principle only, and therefore they are totally different from what we are trying to achieve in the machine learning algorithm. So for that, actually, Wapunik proposed something what is called the structural risk minimization principle. So one can understand that structural risk minimization principle guarantees the uniform convergence of ERM principle to the empirical risk to the two risks actually here. So this was given by Wapnick, and some of you may not know that whatever learning theory we are discussing, and that is the basic learning theory, has been given by Wapnick. He is a Russian statistician, and surprisingly, he published his paper in 1995 only when he migrated to USA. And this work was supposed to be done in late 70s, so sometime 78, 79. That simply means the machine learning theory as such was known already in 1978, 79, but it was known to us or to USA or North America or entire world till 1994 when Wapnick published his first paper. Simply because he was in Russia, things were not known and all those things were there. Otherwise, probably machine learning would have come at least 20 years before. Then it has come in 2010 or 5 or 10 and so on and so forth. Yeah. So this I already explained to you already, so it is just a repetition. So this thing you've done already in the morning class, so I won't go into detail. Yeah. Okay, so what is SRM principle? If SRM principle says that in this family, you choose the function f so that this R empirical f minus this mod here is more than epsilon, and you are taking a soup here. Soup simply because you are taking a soup over this family. That means you are guaranteeing this uniform convergence. So that simply means if somebody says that I am trying to implement SRM principle, that simply means you are guaranteeing me this condition. The difference between the empirical principle and SRM principle is here that in ERM this thing was not there. So that means there it was holding for a given f. In this case, because you taken a soup here, that simply means this is holding for entire f, for entire family of functions f here. And that is simply the uniform convergence. So that simply means if I want to find out machine learning algorithms, then I have to implement the SRM principle. That means I have to choose that f in this family for which this thing is happening, here. Okay. Now again, there is a difficulty here. Difficulty is that because this arc R I cannot compute, and therefore there is no way of computing this probability. And once probability is not known, I cannot find out the limit, etc., and so on and so forth here. So that means again conceptually I am clear, but I cannot implement it because I cannot compute R of f here. So what Wapnick did actually here, that rather than finding out this probability here, he tried to find out an upper bound of it actually here, and that upper bound he tried to minimize. So that means the Wapnick contribution was that he could understood what is the meaning of SRM principle, but then he could realize that this quantity cannot be computed, and therefore there is no way of finding out this term here, and therefore he tried to find out an upper bound on this probability here, and then he suggested to find out that f in this family here, you choose that upper bound over this entire family. Now, how to find out an upper bound? So that upper bound is defined based on something what is called the BC dimension. So BC is the Wapnick's name, and C stands for it's one of the collaborators. So BC dimension tells you that how to implement the SRM principle, and in certain sense it also tells you that what is the compromise between the overfitting and underfitting. It also tells you that how to compromise between model not being too simple and not too difficult. So the first thing to understand is that we will now learn what is the meaning of a BC dimension. Okay, so this is the main question now. How to choose a desired function candidate set F? That means how to choose the family of functions F here. That simply means in terms of machine learning, do you want this family to be the family of hyperplanes? Do you want this family to be a family of circles, hyperbolas in 3 dimension or n dimensions also for here? So how to choose this family of functions? So that will decide that whether the model which you are suggesting is too simple or too difficult. Now, that means you want to understand what is the meaning of size of this family or growth of this family here. And this thing is understood in terms of what is called the Vichy dimension. So we will first define Vichy dimension, then we will not go into the theorem as such, but we will try to understand what is the Wapnick theorem, which gives you an upper bound on the probability which says that ERM principle will converge to SRM principle, SRM in a uniform manner. Now, to understand the meaning of Vichy dimension, you have to understand meaning of what is the meaning of shattering. So, suppose you are given L points here, and you are given a family of function f. Then we shall say that this family Z of L is shattered by this family of functions f, or equivalently, this family shatters Z of L, provided if from this family I construct this training set, then there is always a regression or there is always a classifier. That simply means what we are defining the meaning of shattering. Shattering is always defined for a given set of points. So for a given set of points, you generate all possible data sets. That simply means you take these points and try to define their class labels, all possible class labels, all class possible labels. If given all these data sets, there is a family of functions f which does the exact classification, then we shall say that this family shatters this set, or this set is shattered by this family. So that's the meaning of shattering. So, for example, if you take this set here, x1, x2, x3, so there are 3 points in R2. There are 3 points in R2. And suppose I take the family as the family of linear classifiers, and you want to show that Z3 is shattered by F. What is the meaning of that? From this set, you generate all possible training sets, given the class labels. And if all those possible sets can be correctly classified from a member of this family, then we shall say that this family shatters this class. So, for example, if you take 3 points here, then there will be 8 possibilities. So, all positives, 2 positives, 1 negative, 2 positives, 1 negative, and so on and so forth there. So, in this case, there is a hyperplane is there, hyperplane is there, hyperplane is there, hyperplane is there. And similarly, for other 4, this one is there, this one is there, this one is there here. So that means for our example, there are 8 possibilities, and all these 8 possibilities, there will always be hyperplane which will do the correct classification. And therefore, this family shatters the set of those 3 points, x1, x2, x3. Okay. Now, suppose I take 4 points, and if I take 4 points, and I take again family as this family here, then you can see that is not going to happen. Suppose I take these 2 points here and these points here. So in this case, you cannot classify by a hyperplane, and therefore this family of 4 points cannot be shattered by the family of hyperplanes. That means some sets can be shattered and some sets cannot be shattered. Now, what does Vichy dimension says? We say that this is be a family of functions. Then Vichy dimension of this family denoted by Vichy dimension this is defined as the maximum number of points in Rn which can be shattered by F. So this is our definition of Vichy dimension. That simply means that you choose a family of function, you want to define its Vichy dimension. Its Vichy dimension will be the maximum number of points which can be shattered by this family. So, for example, if I take the hyperplanes in 2 dimensions, then they will shatter at the most 3 points. Similarly, if I take the hyperplanes in n dimensions, then they will shatter at the most h1 points, at the most h plus 1 points here. So we shall say that for family of hyperplanes in Rn, the Vichy dimension is n plus 1 for n plus 1. So there is a theorem. Actually, I'm not giving the theorem, but I think by that example, it must be clear that if you take 3 points in R3, in R2, the family of hyperplanes will shatter. If you take 4 points, it will not shatter. Therefore, the Vichy dimension of straight lines is nothing but 3. Whereas this is also can prove in general. So we can prove this theorem here. So this theorem says that consider the classification problem in Rn. Suppose that this is the family resistance function here. There is a mistake here. This is Rn. Then Vichy dimension of this family is n plus 1. N plus 1 here. So given the family, we can find out whether what is Vichy dimension. There are methods to compute the Vichy dimension, but they are not simple. So again, we know the concept, but not so easy to compute. Now, normally one feels that model is difficult if there are not many parameters. It is simple if there are less parameters. Now, difficulty is in measuring in terms of parameters, at least in machine learning, is not correct because the complexity of the model in machine learning is measured in terms of its Vichy dimension. So if the Vichy dimension is less, the model is simple. Vichy dimension is more, the model is complex. So in machine learning, because I want to do a compromise between the underfitting and overfitting, I must choose a model which is not too difficult and not too simple. That means I should choose a model for which Vichy dimension is neither too high nor low, not too low. Now, there is an example which was to show that number of parameters and Vichy dimension are two different things. Number of parameters does not guarantee that the Vichy dimension will be more or less. So, for example, if you take this family of functions here, there is only one parameter L, there is one parameter L, and if you take L points here, then you can prove that this family will not shatter any of these points here. And because L is arbitrary, so we'll say that Vichy dimension for this family of functions is infinite. So although there is only one parameter, but Vichy dimension is infinite. So that simply means having lesser number of parameters does not mean that model is simple, or having more number of parameters does not mean model is complex. So that is the first confusion which we should try to avoid here. Now this is the main theorem which we understand. So this says, So this says that if we take a family of functions, if we choose a family of functions f, and suppose its Vichy dimension is h, and L is more than h. Remember what is L? L says nothing but the number of data points. So if L is more than h, and L epsilon is more than or equal to 2, then this inequality holds. Please try to understand that I could not compute this probability. So okay, I cannot compute it actually here. So Wapnick said that you cannot compute it actually here. Therefore, you try to find out its upper bound. So this is the upper bound which is provided. So this says that this probability is always less than or equal to this expression here. Now this expression depends upon h, and this depends upon L. And epsilon, of course, you are choosing to be small and so on and so forth there. And therefore, if you want to minimize this, the best thing is that you try to minimize this. If you are trying to minimize this, it depends upon two quantities, namely L and H. L is fixed. The number of data points are fixed. But the only thing is about your H here. So that means if I want to minimize this quantity here, I should try to find out how should to choose my H so that this expression is minimum. Once you do that actually here, then you will know that which family I should choose. And once you know that which family you should choose, then obviously you know how to find out the function f which you want to choose actually here. Now the proof is not difficult, but it is involved. So I will not be proving it actually here. But this is the important theorem which you all must understand, that the Wapnick theorem is based on Vichy dimension. Vichy dimension measures the complexity of the model, and Wapnick's theorem essentially gives you an upper bound on this probability in terms of number of data points and the Vichy dimension. Number of data points are fixed, therefore it depends only on the Vichy dimension. And therefore, in deciding that which family to choose for choosing a function f, I must choose the Vichy dimension in such a manner so that this quantity is minimum. This quantity is minimum. Now, this is another way of expressing the same theorem in terms of data, so I will not do it here. So essentially, this is the same theorem. The proof is it is rewriting here. But this is an interesting thing actually here, because this says this is the true risk which you wanted to find out, minimize. This is the empirical risk. We have seen that empirical risk is not same thing as true risk. It was approximation to true risk for a given f if the sample size was large. But now it says that the true risk is less than or equal to empirical risk plus this term. This is what is called the confidence. So the true risk is less than or equal to empirical risk plus true risk that we have, plus the confidence. This we already know. This quantity is given by this expression here. Delta depends on epsilon. So again, that is known to you. L is known to you. Only again, H quantity is there actually here. So if I want to find out, minimize this quantity here, I should minimize this quantity. This we know how to do it actually here. And this quantity is come. So now we have to do a compromise between this one and this one, between the empirical risk and confidence, or empirical risk and confidence and VC dimension, so on and so forth here. So we can find out the nature of omega H delta. So the right hand side of the equality, namely this one, is called the structural risk. So it's nothing but this one. And statistical risk minimization principle simply says that you minimize this whole thing actually here. Please try to understand empirical risk minimization principle means minimize this part only. Statistical SRM principle says minimize this whole thing actually here. Now in this case, L is known to us, delta is known to us because at fifth epsilon, H is known to us. So H you want to fix in a manner so that the VC dimension is less and so on and so forth here. That means the complexity of the model is not very high. At the same time, it is not very low and all those things actually here. But conceptually, we know that if I want to understand, minimize the SRM principle, I must minimize this quantity here. So ERM principle says minimize this part only, and SRM principle says minimize this whole thing. Okay. So this is your ER. This SRM, the statistical risk is nothing but this is true risk less than statistical risk here. This quantity is nothing but empirical risk is confidence, and then of course these things are there. So this is again what I told already. Now what really happens here is that one can prove mathematically also, but you can see very easily that as the number of data points increase, the empirical risk goes to decreases, and as the data points increase, the confidence level increases, and therefore VC dimension increases, and that means this function goes to this is increasing. So you want to find out this function is decreasing and this function is increasing. And I want to choose something here for which I get this minimum, But it's not possible. So you try to compromise this one or this one here. You take some multiple of this one and multiple of this one and get this function here. And this is what is, you minimize this one here. So in optimization, is what we call the multi-objective optimization problem. So one is the empirical risk, that is the confidence level. You try to generate a objective function, which is a combination of these two, and then you try to find out minimize that. And as we shall see, that this whole process essentially leads to support vector machine. So one thing we can see here is that this confidence level is a infinite function of h. So that by simple calculation, if you find out the delta omega by delta h or d omega by delta dh, you see it is positive. That means the confidence level is a increasing function of h. And that simply means if I want to minimize this thing here, I must minimize h. So this argument shows that to minimize the confidence level, you have to minimize this term, and that means you must minimize h. Yeah. Okay, so I will, yeah. So what you can do here is how to implement SRM principle in a suppose simple situation where you are given a bilateral classification problem, and you are given choose the family as the family of hyperplanes with extra condition that norm W is less than or equal to T. So this is a parametric family of hyperplanes. norm W less than equal to T. So if T1 is less than T2, then this family is contained in this family. I choose the hinge loss function that you must have been told already. I compute the empirical risk. And then I write the empirical risk minimization problem for this family. So we know that what is empirical problem? It simply means that I minimize this one with these conditions, So we can do it here, and we obtain this problem here. So in this case, the empirical risk minimization principle comes out of this form here. Now everything is old. There's nothing very different here, except this last term, norm W is equal to T, because this family depends upon the parameter T. So from here, I will get this term here, but from here, I will get this T as well here. So norm W less than equal to T here. So for every T, I can solve this norm W, and then I can choose the one for which this quantity is minimum, so on so forth here. But again, because you are saying that you solve for every T, which is not possible because T is arbitrary. So you must do something intelligent, and that intelligent thing is precisely this particular theorem of Wapnick. So Wapnick gave this theorem in 1995. So he showed that if VC dimension H of a set of canonical planes in Rn, so this norm is less than equal to T, is this bound is there. If you want to minimize H, then you must minimize T. To minimize T, by previous argument, by how T was chosen, it is same thing as minimize norm W. Minimize norm W is same thing as minimize VC dimension. Minimize norm W is same thing as maximization margin. What will happen that in learning theory, maximizing margin comes afterwards. That means you first deal with the model complexity, get VC dimension, make use of these theorems, and then come to the margin. Whereas if you're not learning a theory, if you're not following learning theory, then everybody will define that you maximize the margin, giving some arguments which are not mathematical, and some certainly correct arguments, but not mathematical. And we'll say that you find out the upper plane for which the margin is maximum. That is correct, but not correct mathematically. Correct approach is that you try to find a upper plane for which the empirical risk is minimum, for which VC dimension is minimum. Minimizing VC dimension means minimizing the norm W, which is same thing as maximization of margin. And therefore, you get the usual SRM formulation. So this is your empirical risk. This is your minimizing the norm W. So it comes from the VC dimension. So margin argument is correct, but usually this term comes from the VC dimension. And because two objective function is conflicting, one is decreasing and increasing, you have to do a trade-off. So this is your trade-off parameter C. So this is a multi-objective optimization problem, and you are doing a trade-off between those two functions and so on and so forth there. Now, of course, you can ask the question that if it is not, I don't want to modify for the hyperplanes, then of course everybody will say that you go to kernel trick. And kernel trick again we do in the class in a very, very naive way. We never tell that from where it is coming and so on and so forth there. And as I told you already, that the kernel trick comes basically from the theory of reproducing kernel Hilbert spaces. And there's a part 2 of this lecture actually here, which deals with that. Actually, this whole lecture is basically in 4 parts. So part 2 deals with the theory of reproducing kernel Hilbert spaces. And then part 3 is mathematics behind neural networks. And part 4 is mathematics of deep learning. So with these 4 parts, we are currently developing a book, which hopefully come at some point of time. And I will discuss with that book with you in remaining time actually here. But let me summarize that what we have done. So we have first tried to understood what is the difference between statistics and machine learning. And what we have seen that inherently statistics is distribution dependent, machine learning is distribution free. So that is the first difference. Otherwise, in terms of concept, in terms of type of problem they study, the two topics are same. But one is distribution free, there will be machine learning, other is distribution dependent. Now, what is different between machine learning and mathematics, which you understand? Machine learning is an inverse problem. Mathematics is basically a direct problem. That means you are given the input, given the dynamics there, I can find out the output. So that means I have modeled a differential equation. If you tell me what is the input, I can find out the output. For example, in physics, simple physics, we all already formula that S is equal to ut plus half ft square. If you tell me what is initial velocity, what is acceleration, I can simply put and find out distance. Whereas in this case, in machine learning, it is the inverse problem. The function is not known to me. Learning simply means determine the function, determine the model, and then make use of that to forecast. That simply means that mathematics inherently is direct problem, machine learning is inverse problem. So that means in simple terms, machine learning is distribution free statistics, and it is an inverse mathematics problem. That's the second thing. Third thing is that in machine learning, we are trying to do a trade-off between underfitting and overfitting, between simplicity of model and between complexity of model. And all these terms we have to understand mathematically. Overfitting and underfitting, again, we tell in the class in a very simple manner without going into the mathematics part of it here. But these are technical terms, and one should understand in terms of the right mathematical perspective. So you want to do a trade-off between the overfitting and underfitting. It is same thing as doing trade-off between the empirical risk and confidence. It is same thing as saying trade-off between empirical risk and the confidence level of the dimensions and so forth here.